Hey everyone, and welcome to the second half of our lecture, part two. I think this one will be a brief lecture. We're going to talk about multiplying matrices by real numbers. And you notice in here I have in parentheses the word scalars. Well, what the heck is a scalar? Let me make it real simple. In most contexts, when we're discussing matrices, a scalar is a real number, and vice versa. So whenever we think scalar, just think of a number on the real number line. So what we're going to be talking about is multiplying matrices by real numbers, or scalars. Let's look at some examples. Here's how we multiply a matrix by a scalar. To multiply a matrix A by a scalar, we multiply every entry of the matrix by the scalar. To multiply a matrix by a scalar, we multiply every entry of the matrix by the scalar. Here's an example. This is the matrix A. Multiply A by the scalar 3. Here's how we do it according to what's written here. We're going to take A and multiply it by the scalar 3. Here's the matrix A. Here's our scalar. And according to what we have written up here, we're going to take each one of these entries in matrix A and multiply each of these entries by the scalar 3. So this is what we're going to get. 3 times 1, 3 times 3, 3 times 5. That's the first column. Now we have to multiply the entries in the second column by the scalar 3. 3 times 2, 3 times 4, 3 times 6. So here's our answer. 3A, or 3 times A, is equal to this matrix. And maybe that brings out another point that I should mention. If we multiply a matrix by a scalar, like we did here, we get another matrix. So a scalar times a matrix is another matrix. And I'll write that down in a second. Just a footnote here. A scalar times a matrix yields another matrix of the same size. Let's do another example. Compute 5A, where A is the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. I don't exactly get an A for imagination, but it'll be an easy example to follow. All we have to remember is this. How do we multiply a matrix by a scalar? We take every single entry of the matrix and multiply it by that scalar. In the first row, we'll have 5 times 1. We'll have 5 times 2. And we'll have 5 times 3. Then we do the same with the second row. In the second row, we'll have 5 times 4, 5 times 5, 5 times 6, and then we move down to the third row. 5 times 7, 5 times 8, 5 times 9, and you might notice that I did this a little bit differently than I did the previous example. In the previous example, I took my scalar and I multiplied column 1 by the scalar. Then I multiplied column 2 by the scalar. Here I did it scalar times row. I did the scalar times row 1, the scalar times row 2, the scalar times row 3. Does it make a difference whether we do it column by column or whether we do it row by row? We can compute the product of a scalar times a matrix by multiplying the scalar times each entry in row 1, then row 2, then row 3. Or we can compute the product of this scalar times this matrix by computing the product of this scalar with every entry in column 1, this scalar with every entry in column 2, and so forth. So whether we multiply the entries row by row or column by column doesn't matter. Voila. So here is my answer. And I think next I'm going to tie multiplying a matrix by a scalar in with adding matrices. And there is a connection somehow. We're going to tie those two things together next. Recall something. We can add two or more matrices together exactly when the matrices are the same size. That is, same number of rows, same number of columns. So let's look at these two. The size of the first matrix, we have, let's see, how many rows? 1, 2, 3 rows. 3 rows, and we have 2 columns, 3 horizontal rows, and 2 vertical columns. What about this matrix? We have 1, 2, 3 horizontal rows, and we have 1, 2 vertical columns. So the size of the first matrix is 3 by 2. The size of the second matrix is 3 by 2. We can add these matrices. Why? Because they're the same size. These two matrices are the same size, 3 by 2, 3 by 2. Our book, I'm not sure, it may use the expression same dimension. They might use that. If they say the dimension of the matrix, they're saying 3 by 2. These are the same size, the same dimensions. We can add them. And I'll tell you what, since we have these two matrices up on the board already, I know we know how to do this, but let's do it anyway. Let's just add them together. Now, do you remember how it is that we add two matrices? We take the corresponding elements of each row and column and add them together. This is first row, first column. We'll add it to the element over here that's in the first row and the first column. So in our sum, we'll have the sum of the entries that are in the first row and first column, first row and first column. And this will be the entry in the first row and first column of the sum of the two matrices. Now let's do this. First row, second column, first row, second column. Let's add those. Okay, bingo. We got the first row of our matrix. Second row, first column, second row, first column, 3 plus 4. Second row, second column, second row, second column, 4 plus 5. Okay. Third row, first column, third row, first column, 5 plus 8. Third row, second column, third row, second column, 6 plus 9. And holy moly, I'm going to have to put my answer down here. We get 3, 7, 15. And 5, 9, 15. Really? How about 3, 7, 13? And 5, 9, 15. There is our answer. That's 8 plus 2. Now remember, I said that I was going to tie all of this into multiplying matrices by scalars. That's still my objective. I'm just reviewing what it means to add 2 or more matrices together just so that we can tie everything together. Let's look at another example. Similar example. Let's see if we can add these 2 things together. We can add them together provided they are of the same size or have the same dimensions. Let's see. This has 1 row, 2 rows, 3 horizontal rows, and 1 column, 2 columns. So the size or dimensions of this matrix are 3 by 2. Now let's look at this son of a gun. 1 horizontal row, 2 horizontal row. That's 2 rows. And let's see. 1, 2, 3 vertical columns. Can we add these together? No, we can't. They're not the same size. Not the same size or the same dimensions. So we can't add them together. Son of a gun. Now, some of you may be looking at this and say, wait a minute, can't we add those? This thing and this thing are the same. Now, that's a good observation. The number of columns of the first and the number of the rows of the second are the same. But does that mean that we can add them? No. What it does mean is that we can multiply these together. Oddly enough, we can multiply these 2 matrices together because the number of columns of the first is the same as the number of rows of the second. We can multiply these together. But oddly enough, we can't add them together because the sizes are different. 3 by 2 is different than 2 by 3. We can't add them together. So if you are looking at this and saying, wait a minute, why can't we add them together? This number is the same as that number. If this number is the same as that number, we can multiply them together. But Unless the size of each is the same, we can't add them together. So these two things we can't add together. And let's keep our eyes on where I'm going. I'm going to relate adding matrices to multiplying matrices by a scalar. That's where we're going with this. Okay, let's consider this. Can we add a matrix to itself? Here's the answer. We can always add a matrix to itself. And why can we do that? Because every matrix is the same size as itself. If A is 3 by 2, and we add A together, we're adding two matrices of the size 3 by 2. We can add them together. Let's look at an example here. Let's add A to itself. A has 3 rows and 1, 2 vertical columns. So yes, A is the same size as itself. We can add A to A. And we take the entries in row 1 and column 1. 1, 1. Then we take the entries in row 1, column 2. 2 and 2. And then we'll take the entries in row 2, column 1. Row 2, column 1. The entries in row 2, column 2. Row 2, column 2. Row 3, column 1. Row 3, column 1. And row 3, column 2. Row 3, column 2. Okay, there we have it, A plus A. And I'm going to encapsulate my answer down here. A plus A equals, what was it? 2, 4, 6, 8, 10, 12. And some of you may have noticed something. This matrix here, A plus A, is the matrix that we would get if we took the matrix A and multiplied it by 2. Let me make room for that. working with the same matrix here. Let's see, can you see that? Yeah, I guess you can. Same matrix, we're going to compute 2A. And how do we get this? Don't we take every element of matrix A and multiply it by the scalar 2? So we'll have 2 times 1, 2 times 2, 2 times 3, 2 times 4, 2 times 5, 2 times 6, and that just happens to equal 2, 4, 6, 8, 10, 12. That's 2A. And to our amazement, this is the same matrix as this. This is A plus A, and this is the matrix 2 times A. They are one and exactly the same thing. So if we take a matrix and multiply it by a whole number like 2, what are we really doing? We're adding the matrix to itself twice, A plus A. Should this shock us? Well, let's see. This shouldn't shock us. We added matrix A to matrix A, and we got 2A. Given a variable x, x plus x is 2x. X plus x plus x, that's 3x. If we add x to itself 4 times, we get 4x. Well, the same exact thing happens when we add a matrix to itself. Given the same matrix A, whoops, adding a matrix to itself 3 times is the same thing as multiplying the matrix by the scalar 3. And this is what we get. You don't believe me? Well, just this one more time. Let's check and make sure that it really works. let's see what we get here. We take the element in the first row and first column of each matrix and add them. First row, first column, first row, first column, first row, first column. So that's 1 plus 1 plus 1. Then we do the same thing with the first row and the second column. First row, second column, first row, second column, first row, second column. And then we take the elements in the second row and the first column and add them together. Second row, first column, second row, first column, second row, first column. And then we take the elements in the second row and second column. Second row, second column, second row, second column, second row, second column. And then finally, we'll take the elements in third row, first column, third row, first column, third row, first column, third row, first column. And third row, second column, third row, second column, third row, second column, third row, second column. And if we add these all up, we get 3, 6, 9, 12, 15, 18. This is A plus A plus A. And it turns out to be the same A plus A turns out to be the same as 3A. So whenever we have a matrix multiplied by a positive whole number, that's the same as adding the matrix to itself the same number of times as whatever the positive whole number is equal to. Now, let's do some homework exercises that are sort of related to this. This looks like a good example. Given the matrix A and B, compute 3A plus 2B. We know how to do this. Let's do it. 2A plus 3B. So far, so good. Now, just because we're working with matrices doesn't mean that the laws of arithmetic and algebra that we grew up with have changed. They haven't. And in this example, we have multiplication 2 times a matrix, multiplication 3 times a matrix, and we have addition, this plus this. What do we do first? The rules haven't changed. The rules have not changed, and there are no parentheses here to change the order in which we do the operations. So if we have multiplications to do and we have additions to do, which do we do first? Multiplication, you're right. So we got to multiply these babies together. And we have 2 times 1, 2 times 2. 2 times 3, 2 times 4. 2 times 5, 2 times 6. Okay, that is 2a. Now let's go over here and do this son of a gun. 3 times the first row, 3 times 2, 3 times 4. So that's going to be 6 and 12. And then we have 3 times the second row, 3 times 6, 3 times 8. So that's going to be what? 18 and 24. 3 times 6 is 18. 3 times 8 is 24. And now we'll do 3 times the third row. 3 times 10, 30. 3 times 12, 36. Beautiful. That's 3b. Excellent, excellent, excellent. The only thing that's left to do is to add these two things together. And can we do that? Yep. This is 3 rows, 2 columns. So this is 3 by 2. This is 3 rows, 2 columns. This is 3 by 2. They're the same size or the same dimensions. So you bet we can add these two things together. And we take the elements in row 1 and column 1, 2 plus 6. And then we go to row 1, column 2, 4 plus 12. Now let's go down to the second row. Second row, first column, 6. Second row, first column, 18. Okay. Second row, second column, 8. Second row, second column, 24. And finally, third row, first column, 10. Third row, first column, 30. Third row, second column, 12. Third row, second column, 36. Voila! This is our answer. This is 2a plus 3b. One more example, kind of like this, except we're going to subtract instead of add. But just for the sake of making sure that we've done an example like this, we're going to do it once. Very similar kind of exercise as the previous one. The only difference really is that we're going to be subtracting these two things. But other than that, no difference. Let's have at it. So here's 3A, and here's 2B, and we're subtracting. And again, we have multiplication, 3 times a matrix, 2 times a matrix, and we have subtraction. The rules of algebra haven't changed. If we have multiplication and we have subtraction, which do we do first? The rules haven't changed. We do multiplication first, don't we? So let's have at it. Multiply 3 times the first row, 3 times 1, 3 times 2. So that's 3, 6. 3 times 3, 3 times 4, that's 9 and 12. And 3 times the last row, 3 times 5 is 15, 3 times 6 is 18. And this is 3A. Now we still haven't done this multiplication yet, so let's do it now. 2 times the first row, 2 times 2, 2 times 4. That's 4 and 8. 2 times the second row, 2 times 6 is 12. 2 times 8 is 16. And 2 times the elements in the third row. 2 times 10 is 20. 2 times 24. I'm sorry, 2 times 10 is 20. 2 times 12 is 24. That's 2B. The only thing left to do is subtract these two son of a guns. And we do first row, first column, minus first row, first column. So that's 3 minus 4. And then we do first row, second column, minus first row, second column, 6 minus 8. Let's do the second row. Second row, first column, minus second row, first column, 9 minus 12. Second row, second column, 12, minus second row, second column, 16. And finally, the third row. Third row, first column, 15. Third row, first column, 20. Third row, second column, minus third row, second column, 18 minus 24. There's our answer. This matrix is 3A minus 2B. And I'll encapsulate our result down here. Bravo. Now let's hit the homework, everybody.